This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today we're delving into a paper titled Of Good Demons and Bad Angels, Guaranteeing Safe Control Under Finite Precision. This research tackles a critical challenge in the field of safety-critical neural network-controlled cyber-physical systems, and NCSS. The authors addressed the discrepancy between theoretical safety guarantees and real-world implementations affected by finite precision. What's the core problem this paper aims to solve?
The core problem is the disconnect between the idealized, real-valued mathematics used to prove the safety of NCSS and the realities of finite precision computing in actual hardware. Existing methods, like Versa, offer strong, infinite time horizon safety guarantees, but these rely on perfect, real-number arithmetic. In practice, round-off errors in sensing, actuation, and computation can accumulate and lead to unsafe behavior, invalidating the theoretical guarantees.
Versailles is mentioned as a significant prior work. Can you elaborate on its limitations in the context of this new research?
Versailles provides robust, infinite time horizon safety verification using differential dynamic logic (DL). However, it operates under the assumption of real-valued NN semantics, ignoring the impact of finite precision arithmetic. This paper extends Versailles to account for these real-world limitations.
The paper introduces the concept of a good demon and a bad angel. How does this game theoretic framework address the finite precision problem?
The good demon represents the control actions, striving to maintain safety. The bad angel introduces bounded perturbations representing round-off errors, sensor noise, and actuator inaccuracies, attempting to push the system into an unsafe state. This framework allows for formal proofs of robustness against a given level of perturbation.
This sounds like a hybrid system approach. How does the paper integrate continuous and discrete dynamics?
The system is modeled as a hybrid system using differential game logic, DGL, which naturally handles both continuous physical dynamics and discrete control actions and perturbations aspects. The DGL framework allows the authors to express the interaction between the good demon and the bad angel as a game, where safety is defined as the demon having a winning strategy.
The paper mentions the use of differential game logic DGL. How does DGL differ from differential dynamic logic DL, and why is it suitable for this problem?
DL is a logic for reasoning about hybrid systems, while DGL extends DL to handle adversarial dynamics, which is crucial here. The adversarial nature of the problem, the good demon versus the bad angel, makes DGL the appropriate tool for formalizing and verifying robustness. DL alone cannot capture the adversarial interaction.
The paper proposes a decidable criterion for robustness. What makes this criterion decidable, and what are its limitations?
The decidability comes from leveraging existing real arithmetic SMT solvers. The criterion is sufficient, but not necessary. A failure to satisfy the criterion doesn't definitively prove non-robustness. A stronger loop invariant might be needed to prove robustness in some cases.
How does the paper integrate mixed precision fixed point tuning into the overall verification process?
Once a control envelope is proven robust to a certain level of perturbation, the authors use a tool like DAISY to synthesize an efficient mixed precision fixed point implementation of the neural network. DAISY aims to minimize resource usage while ensuring that the implementation's errors remain within the previously determined perturbation bound.
The paper evaluates its approach on several case studies. What were the key findings from these evaluations?
The case studies, including adaptive cruise control, ACC, and a vertical airborne collision avoidance system, VCAS, demonstrated the practical applicability of the method. They showed that even seemingly safe control envelopes can become unsafe under small perturbations, highlighting the importance of robustness analysis. The approach successfully generated efficient fixed-point implementations with rigorous safety guarantees.
What are the key contributions of this paper, and how does it advance the state-of-the-art in NNCS safety verification?
The paper's main contributions are threefold. 1. Formalizing robustness for control envelopes under perturbation using DGL. 2. Providing a decidable criterion for guaranteeing infinite time horizon safety under perturbations. And 3. Integrating precision tuning to synthesize efficient fixed-point implementations. This work bridges the gap between theoretical guarantees and real-world deployment, significantly advancing the field of NNCS safety.
The paper mentions limitations. Can you elaborate on these limitations and potential future research directions?
The main limitation is the incompleteness of the robustness criterion. A failure to prove robustness doesn't necessarily imply non-robustness. Future work could focus on developing more complete criteria, exploring different perturbation models, and extending the approach to handle more complex NN architectures and control systems. Improving the scalability of the mixed precision tuning process is also a key area for future research.
How does this work compare to other approaches in NNCS safety verification?
Many existing methods either ignore finite precision effects or only provide finite time horizon guarantees. This paper distinguishes itself by providing infinite time horizon guarantees while explicitly accounting for finite precision errors. It builds upon Versailles but addresses its limitations regarding real-world implementations.
The paper uses DAISY for mixed precision tuning. Are there alternative tools, and what are their strengths and weaknesses compared to DAISY?
Yes, there are other tools like Aster, Popix, and 5-Tumor. DAISY's strength lies in its sound error computation and integration of expression rewriting. However, it has limitations in handling complex NN structures. Aster, for example, is more NN specific but has limitations in precision and scalability. The choice of tool depends on the specific needs of the application.
In summary, what is the most significant impact of this research on the field of safety critical systems?
The most significant impact is the advancement of practical, verifiable safety for NNCS. By bridging the gap between theoretical guarantees and real-world implementations, this research contributes to building more trustworthy and reliable autonomous systems. It provides a concrete methodology for ensuring the safety of these systems in real-world scenarios where finite precision effects are unavoidable.
The paper focuses on neural networks. Could this methodology be extended to other types of controller?
Yes, the core methodology is not limited to neural networks. The framework of a good daemon and a bad angel, along with the use of DGL, is applicable to other types of controllers as long as their behavior can be formally modeled and verified. The specific techniques for implementation synthesis might need adaptation, but the fundamental approach remains generalizable.
The paper uses Chimera X for the DL and DGL proofs. What are the advantages and disadvantages of using Chimera X for this type of verification?
Chimera X is a powerful theorem prover specifically designed for hybrid systems. Its advantages include its support for DL and DGL, its interactive proof environment, and its integration with various SMT solvers. However, it can be computationally intensive for complex systems, and the interactive nature of the proof process requires expertise in formal methods.
The paper mentions the use of N3V for neural network verification. How does N3V contribute to the overall verification process?
N3V is a crucial component, providing the means to verify that the neural network implementation satisfies the safety specifications derived from the robust control envelope. It leverages existing real-valued NN verification tools and techniques, making the verification process more efficient.
The paper highlights the importance of considering perturbations in both the input and output of the controller. Can you elaborate on why both are crucial?
Perturbations in the input, sensor noise, can directly affect the controller's decisions. Output perturbations, actuator inaccuracies, or computational errors can cause the system to deviate from the intended trajectory, even if the controller's decision was initially correct. Considering both is essential for a comprehensive assessment of safety under finite precision.
The paper uses Xilinx Vivado for FPGA synthesis. Why is FPGA synthesis important in this context?
FPGA synthesis is crucial for deploying the verified fixed-point implementation onto hardware. FPGAs offer the performance and resource constraints often required for safety-critical embedded systems. The use of Xilinx Vivado ensures that the generated code can be efficiently implemented on a real-world platform.
The paper mentions the use of pre- and post-processing steps to adapt DAISY to the specific structure of neural networks. Can you elaborate on these steps?
DAISY doesn't natively support the common structures found in NNs, vectors, matrices, loops. The pre-processing step unrolls these structures to make them compatible with DAISY. After DAISY performs the mixed precision tuning, the post-processing step reintroduces the original structures, resulting in more efficient and readable code.
This has been a thorough discussion of a very important paper. Thank you for your insightful explanations.